Okay, hello. Today is June 30th, and this is the last session before the, it's not the first exam, it's the second quiz, okay? So our plan is to share with you an example. It's a simplified one, but probably you can at least have a 1 point so you can compare your result with the one that I'm going to show here. And I don't know, is there any questions about the assignment? Yeah, I can answer at the end. The exam is next week. We have to be certain, we have to be sure that the date and time of the exam, we have agreed on that, okay? According to the original schedule, the exam will be given to you on Friday. And it's at the same time as the original, so it's 10:30 in the morning. That's what I understand, okay? If you have problems, anybody has problems, maybe we can agree. We need to all agree, right? We are 20 people. If we all 20 people decide to move it, yeah, we can do it. But that's something that we all need to agree on that, okay? So let's do it, okay? So can you see my full screen? Isaac, can you see my full screen?
Yes.
Okay, so this is the example that I have I developed last year, okay? It's a simplification. Here I have a hull, which doesn't have a constant beam. It has a quadratic variation of the beam, okay? And also the shape of each section, okay? It's a semicircle, right? Okay, so we have located here, the origin of the reference system. And so you see that at the aft end and forward end, beam is 0. And you can see that in the midship section, the area is larger than here at L/4 and larger than here, L/8. Okay, so at the end here, area will be 0. Okay, since it is semicircular, so the beam corresponds to the diameter. So the area is going to be half of the area of a circle. So it's b squared divided by a. Okay, this varies along the length. So we can easily calculate the section coefficient. Okay, so it's going to be this divided by 2b squared, right? Because the beam, I'm sorry, it's b squared divided by 2. Okay, so the section coefficient is going to be p/4. Okay, so that's constant because the beam changes and also the area changes. So that's that. So area changes, section coefficient doesn't, beam changes, and draft changes. So that's that. For this numerical example, these are the numbers that I'm going to use. 45 meter long, 10 meters in beam, so it is 4.5. And this is typical, okay? Beam to draft equals 2.5. Well, this should be beam to depth, but in this case, I'm just going to take this number here. And this is the velocity. Okay, this is in meters per second. Probably it's about 12 knots, right? So if I divide this by 0.51, I should get the velocity in knots. Okay, now, after we have this, we can integrate and we can obtain hull characteristics, okay? Now, let me go back. I didn't mention, but it's floating with no trim, okay? So let me put it here. Okay. So since there is no trim, this is a quadratic and each section is semicircle, then it is symmetric with respect to midship. So the center of gravity is here, okay? So xg is going to be 0. In this case, these are the whole characteristics. We can integrate. This is, I think it's 2/3 LB. So yeah, divided by 3, that's 15. Yeah. The inertia, okay, we have to integrate, okay. This is just the integral of x squared b of x dx from minus L/2 until L/2. This is the mass, okay. So we have the area here, and we can integrate from aft forward and multiply by the density, and that's what we have. So it's about 1,000 tons. This is the second moment of the mass distribution. So this thing here is similar to this one, okay? And finally, after we calculate this, okay, we divide by m, okay? So kyy squared is the inertia divided by the total mass. And if we get the square root of that, we can divide it by the length, and this is the percentage that we are taking. So more or less, okay, from here to here, that's 0.5, that's 0.25, so it's about here. More or less, from here to here, that's the radius of gyration. Makes sense, because we see that there is more mass here than toward the ends. So it's about 0.25, this is 0.22, so it's very close to that. Okay, you can see that we have to be careful because this is the mass, okay? In this case, the first moment of the water plane is 0 because it is symmetric, okay? So in this case, this is a special case, the two problems will be uncoupled, okay? Heave and pitch will be uncoupled. Any questions about this data, this information? Any questions? No? Okay. So let's proceed with the calculation. Okay. So hydrostatics is basically this, right? So area times gamma will give you C33. Inertia times gamma will give you C55. And C35 is 0 because it's symmetric. Xg is 0. So here we have all the the static coefficients. Now let's go to the dynamic coefficient, the hydrodynamic derivatives, okay? And that means other mass and damping coefficient, okay? Now, there are many ways that you can do it. This is one way, okay? Now, since we are facing a symmetric hull, there is no point in integrating over the whole length. So what I'm going to do is I'm going to take advantage of that, right? So I'm going to integrate from here until here, and then the result is going to be doubled. Okay, so I'm going to take 4 evaluations, here, 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 and at the end, and I'm going to proceed to do the evaluations, integrate. In this case, I'm going to use the second, what's the name of the numerical integration scheme? Simpson rule. So I'm going to use the second Simpson rule, 1, 3, 3, 1. And then the results are going to be doubled, okay? So this is the X position. Remember, X0 means you are in the midship here, and then you go forward. So this is L/2. So here, this I evaluated the beam. It has a quadratic variation, okay? This is a quadratic variation. You see that from here to here, the reduction is 1 point something, and from here to there, the reduction is 5.56. So this is not linear variation. Now, this calculation is specifically for one value of lambda. This is the wavelength, okay? So I take 67.5, which is about 1.5 times the wavelength, the ship length. Ship length is 45, okay? So it's basically 1.5 the ship length. With this, I can calculate K, 2 pi over this, and with that, I can calculate omega sub 0. So this is the wave frequency. This is radians per second, okay? Now, since we're moving with velocity, I have an encounter frequency, which is different than 1. Let's ask somebody. Mr. Astudillo, do you remember the expression for the encounter frequency?
The encounter frequency is frequency minus
Don't look it up. Try to
velocity. K for cosine the angle.
Exactly. Ku cosine of the angle.
Yeah.
Okay. So, Mr. Zamora, if we're receiving the wave from the bow, okay, what is the angle in this case between wave and the motion of the ship? What's the angle in this case? We're receiving waves from the bow. In this case, Mr. Zamora, beta is what? No? Miss Gutenberg, what is the value for beta? Miss Gutenberg? No?
Yes, doctor, I'm sorry. Is 180 degree?
Yes. So in this case, cosine of beta is equal to -1. And omega of encounter is equal to not the frequency of the waves plus Ku. Okay. So we have the natural frequency, we have lambda, the velocity was 12 knots, so we can calculate the encounter frequency.
See?
Okay. Now, with this encounter frequency, we can proceed and calculate the non-dimensional frequency, okay, at each one of these points. Okay, and you see that we go from 1.19, 106.66, and finally, at the forward end, since the beam is 0, this parameter is 0. Okay, so it's a good, I mean, it's good to have this value, right? But we need it because that means that we close the curve in that point. So 0 is a good value, okay? With this, what's the ratio between B and T? What's the ratio between B and T in this case for any of these sections? Mr. Manrique, what's the ratio between B and T in this case? Mr. Manrique?
Yeah, depend of the length.
Come on.
B,
Come on,
T,
Mr. Enrique. Mr. Matute, what's the ratio between B and T in this case for any section? Mr. Matute, turn on your camera, please. Now,
0.4?
Yeah, what's the ratio between B and T?
0.4? No?
No. B and T, B over T. Miss Hidrobo?
1?
1?
I'm not sure.
Mr. Barba, what's the ratio between B and T?
Is 0.8.
This is the section, okay? So it's semicircular. So from here to there, that's the diameter, and it's equal to the beam. What is this? This is the draft. Ratio of this with respect to that.
5/4.
It's 2.
2 to 1, so it's equal to B over 2. So what's this ratio?
2.
Yes. So we have section coefficient, okay, which is P over 4. And then we have B over T, which is equal to 2. So we can proceed and calculate the C and A bar to calculate A33 and B33 for each one of the sections, specifically for this wavelength. This is what I have here, okay? For each section, I have the section, the C coefficient, okay? And the A bar coefficient, okay? And that's for this and aspect ratio for each section of 2. Okay. So we see that this value is decreasing. Okay. And this value, it increases or decreases up to 0. And then we can apply the formula for A33 and B33. Please, this is very important. Okay, this is very important. Okay, so we have to keep track of these coefficients, each one in its corresponding units. Very important. So every time we do these products, these operations, we should keep track of the units. And then what we have to do is we have to integrate half of the length and then multiply by 2. This is what I'm doing here. So in this line, I have the Simpson factor 1331. And what I do is I multiply this times that, and that's what I get here. This times that, that's what I get here, etc. Similar for B33. Okay, so this is going to be what? This is going to be the integral. So I add this. Do you remember the Simpson factor for the second Simpson rule? What's the factor, not the coefficients?
3/8.
3/8.
Exactly, 3/8. So this is 3/8 summation delta x and multiply by 2. That's this value here. So what is this value at the end?
The added mass.
Exactly. So this is A33. And this thing here is B33, damping coefficient. So what are units of B33? Big B33. What are units of this?
Vertical.
Force per
units.
time over length.
Exactly. So it's force times over length in this international system of units. So you multiply this by velocity and you get force. Okay. A33 kilograms. You multiply this by acceleration and get newtons. But you also need the properties for the pitch. Okay, in that case, you use the same A33, okay? So you use these values, these two values here. But now you are integrated, multiplied by the square of x. Okay, so I have x here. I can square it, multiply by this, multiply by Simpson factor to integrate, and that's what I have here. So here I have 7.5 squared times 20,000 times 3, and that's this. etc. At the end, the beam is 0, so these two are 0. Similarly for the damping rack. And these equations are the same. So this equation is the summation times 3/8 times delta x and times 2, because this is just integrated from 0 from midship until the forward end. Since it is a symmetric case, we double that, and this is what we have here. So what is this? What is this value here?
855.
Exactly. This is 855, which is the correspondingly, this is B55. Okay, so the only difference between the first two values and these last two is that these last two were multiplied by x squared. So that means that this has units of this times meter squared. In this case, this will be newtons meters second. See that you multiply this by acceleration, okay? And you should get newtons meters. You multiply this by velocity, 1/2, and you get Newton meters. See, units are very, very important. Questions about this process, people? Any questions about this process?
Doctor, questions.
Yeah, go on.
It's about the 835 and B35.
Yeah.
In this case, we don't use because it is symmetric.
Yeah.
Respect to the X direction.
Midship section. Yeah. See those. Okay. Let's see if I have this. Okay. For example, 835 is equal to the integral. I don't remember the sign. Okay. It's equal to x 833 dx. Okay. So, but this thing here, 833 at x position is equal to 833 at minus x position. So when you integrate, you get 0. So that's equal to 0 in this case, which is a symmetric Hull. When it is not the case, then you have to obtain a certain value, which is different than 0.
Okay, doctor, thank you.
Okay, so this is a simple case because it was an example, right? So I wanted to save some time. That's why I chose this shape. Okay, now we have the static derivatives. We had the dynamic derivatives. We still need to calculate the excitation, okay? And in this case, I'm going to calculate both the Frode-Krylov and the diffraction term. So just to remind you, here. So this is the term that I'm going to use. Okay. So we have these two. I have A33, I have B33 divided by frequency. That's this thing here. But then I have to multiply by cosine plus I sine. So I have to be careful with this. And then this is also depending on the position of x. Okay, but this is real. So I have to do the product e to the ikx times these two. And so I have to identify real and imaginary parts And I have to integrate both parts by separate. Okay, and at the end, I'm going to put them together, okay, to form a complex excitation amplitude. So that's what I'm going to do in the here. Okay, so for the wave excitation, okay, the first part of the table is the same, okay? Here, I have the A33 and B33. I didn't have enough space, so I'm just, see, I have it from here. So I need this part here. Okay, then I have to evaluate cosine and sine, kx. Remember that this x is changing, so these terms are changing too. Then I have rho, that's the density, rho GB. This term, do you remember where do I need it? Rho GB, do you remember where do I need this term? Rho GB, anybody? Do you remember where do I have this term?
The Kirchhoff term.
For the Kirchhoff term, yes. Okay, and that depends on the beam on this thing here. So you see that it is different. And at the end, since I have no beam, this term is 0. Okay, so that's to calculate the Kirchhoff. And then I need to calculate also the diffraction term. So I need to evaluate this, e to the a kt star. Okay, now remember that this term here, we have to evaluate it at every section. Okay, so we have this. Okay, this is B, which depends on X. Okay, so we know the area. And once you have the area, there are some ways, but the most common way to define T star is equal to the area, which we have here, and we divide it by the beam. Okay, so we should get something about here, more or less. But since this is Z positive, this value is negative. Okay, and that's what we see here, that we have a value which is less than 1, because we raised the exponent to the negative power. That's why it's less than 1. So okay, we have this, and finally here, since there is no beam, okay, there is no beam, there is no nothing, so T star is 0. So e to the minus 0 is 1. That's why we have it here, 1. Have to combine all the real terms, F3, all the imaginary terms for F3. And for F5, remember that we need an arm. So we need to consider the position of every section. In this case, the X is 0. That's why these two values are 0. You see that there is some difference. Okay, so that's that. Now, remember that basically F3 multiplied by minus X give you F5 integrated. So these two are positive, these two are negative. Negative, positive, positive, negative. 0, 0. And here we have the integration. So we add, multiply by 3/8, multiply by delta X, and that's what we have here. Okay, it's possible that we have some terms which are common, and I just employed here. Okay, but this is the process, one way to do it. I mean, there are many ways to implement it. In this case, we have a spacing of what? of points or 1/6 of the length, okay, for the integration. Maybe it's a little bit too much, but it's not so bad. Questions about this process, people? Questions about this process? No? No, okay. So right now, these two here, the two terms will form the amplitude of the excitation. So this is F3 real plus I F3 imaginary. So this is the real part goes here, and this is the imaginary part which goes here. Similar, this is for the F5. Real and imaginary. So right now we have everything. We have static, inertial, hydrodynamic, excitation. So we have to put everything in one single system of equation, 2 by 2, and then proceed to solve. That's next step. So that is the equation that we are going to obtain. In this case, since we are working with the symmetric Hull, this is 0 because symmetry. Similarly, this one here. So in this case, specifically in this case, zeta 3 bar is going to be equal to F3 divided by D11. Both are in general complex. Similarly for zeta 5, the F5, we write it like an F with the force, but it's really a moment, right? And we divide it by D22. Specifically for this case, which is a symmetric case, it's a little bit simpler case. Okay, so these are the values that we obtain. So this is D11, 0, 0, because it's symmetric, and this is D22. Okay, this and that both are complex. This and that are F3 and F5, okay? And they both are also complex. And here, this is the quotient between this divided by that. This is this operation. But since both are complex, we have to use a special operation, a special function in Excel. Similarly for this one. Do you remember the function that you have to use in order to get the quotient of two complex quantities? Anybody? What's the name of the function that you need to use?
Inductor,
MDiff.
imaginary diff.
Exactly.
MDiff.
I'm the. And you said one number and then comma the other. Yeah, thank you. So and the result of this is another complex. This is what we have here. And finally, this is the amplitude. This is a real amplitude. So here I have zeta 3 real plus I zeta 3 imaginary. This thing here is just the absolute value of zeta 3 and the absolute value of zeta 5. These are meters, these are radians. 0.19 meters, that's about this. Radians, so you have to multiply by 50 to get degrees. Questions about the process, people? Questions about the process?
Doctor, I have a question about
Yeah.
the C values. It is because the symmetry is respect to the y-axis, right?
Yeah, to the y-axis, yes, respect to the transfer. This any integral of the first moment are going to be equal to 0. Similarly, for example, if you get the C35, okay, so it's equal to x b of x dx, and in this case, b of x is equal to b of minus x. So it's like saying you are multiplying one function which is symmetric. So it's like that. But you multiply by x, but x is anti-symmetric. So this product give you positive value, and this product give you negative value. But they are the same in absolute value. So if you add this, which is positive, with that, which is negative, the result is 0. Mr. Zamora?
I got you, Doctor. Thank you so much.
Okay, so that's the result. And finally, what you have to do is remember that something that we have insisted is that this process, people, this process, you did it in the first assignment. You did all of this. The main difference of what you did in the first assignment and this assignment is that in this case, most of these parameters depend on the frequency. So you change the length of the frequency of the wave and everything changes. Well, not everything, but hydrodynamics changes. So other mass, damping coefficient, excitation, all of these depend on frequency. So you have to recalculate A33, B33, integrate a second moment, and that influences the excitation. All of this has to be recalculated. And then solve the same system of equations, but with different coefficients. So the response will be different. Okay, here, what I've done, I have changed, that's something that you have to do. I have changed the length of the wave. Okay, so let me go back. Oh, here it is. The lambda in this case is 67.5. So it's about 1.5 times the ship length. Okay, so here I have a series of values. Okay, so since the ship length is 45, this is 0.5 of this. And then this one here is twice this one here. Okay, so what I just showed to you is this line here. Okay, so this value here, it's should be this one here. Probably the amplitude, I just changed it to this value. But that should be. Similarly for zeta 5. And here, what I did was I changed the units. So these are radians, I changed it to degrees. Since it is more physical to have an angle in degrees rather than in radians, right? And then I'm going to plot it. That's the response. So in here, I have the wavelength. Here, this is zeta 3. This is zeta 5. You see that we have a resonance. Usually, the natural frequencies in this case, HEAV are very close. It's usually the case. Okay? And that's why, for example, when we do the tests, remember, we model from springs, okay? We try to put a mass, an extra mass on the aft end, right? Why? because in that case, the two natural frequencies, heave and pitch, tend to separate a little bit more. And with our test, we are able to differentiate between them. But in general, they are very close. Okay, in this case, they are, of course, very close too. Okay, so if we get more values around 50 something, it is possible that we can recognize the difference. But in general, they are very close. If they are not the same, they are very close. Okay, and that's what I want from you. Questions, people? Questions? Questions?
Sorry, I just want to ask you about the.
I can hardly listen to you. I can hardly hear you. Could you please get closer to the microphone, please?
Hello, can you hear me now?
Yeah.
Okay. I want to ask you about the other slide when you show the matrix.
This one?
I get lost. What's the D matrix and what's the other one? Sorry.
This matrix, remember what we did was, okay, the equation that we had in general was something like this, okay? So we have mass plus added mass multiplied by eta 3 double dot plus B33 eta 3 dot. And at the end, well, here we have A 35 eta 5 double dot. And at the end, we have F3 e to the I omega t. And then we said, okay, eta 3 is equal to an amplitude, which in general we consider as a complex. That means that it has a value and also have a phase shift against any references that you want, and times e to the I omega t. We replace into here, and you see that here I have minus omega squared, but it's a real term. This produces an imaginary term, right? So in general, these here are multiplied by eta 3, by this one here. So I have minus omega squared m plus A33 plus I omega B33. And all of this is multiplied by zeta 3. And then we go multiply by zeta 5. And on the right-hand side, I have F3. Because in each term, we have this E omega t, so we can cancel. And this is what we have here. So D11 is just everything here. So you see that it has a real part and an imaginary part. And here, I'm sorry, I'm missing something. I'm missing here. It's C33. It's real also. So we better put it here. So there. Okay. So all of this in this big parenthesis is what we call D11. Okay. In this case, since it is a symmetric Hall, all of these give you 0. That's why I marked this as 0. We have another equation for the pitch. And again, we have 0 here, and we have something similar to this multiplied by zeta 5, and that's D22. Mr. Zamora?
Yes, and I just want to know.
Okay.
Sorry, can I break? This is the D matrix, right? This is D inverse.
No.
I'm just gonna get
no,
the names of
no,
these.
this is the D matrix. This is the F vector. So this is F3, this is F5. Okay, this is zeta 3, zeta 5. And these are the amplitudes. So this is the amplitude of zeta 3, and this is the amplitude of zeta 5.
Okay. Thank you, doctor. I got you.
No problem. No problem. Do you remember, does anybody remember the name of the function? So you get the amplitude of a complex number?
I think it's in the absolute value.
In ABS, okay. So you get in ABS parentheses, and you put and you signal this number here, and you get the imaginary part, the real amplitude. Any other question, people? Other question? Okay, it's 5:04. I don't want to make a break here. Let's ask, for example, how many groups do we have in here in this class, Isaac? Isaac, how many groups do we have in this class? It's 8 or 9? 8. Okay, let's go to group 4. Who is in group 4?
Doctor, me and my classmate, Jordan Ramon.
Okay, how far have you go?
Yeah, okay, we obtained the forces in preload and diffractions, and today we are doing the amplitude and of heat pitch.
Okay.
Obtained.
Okay, so hopefully with this example, you are able to complete this exercise. Okay, and then what I suggest is that it's something that I did, but it's implicit in this example, is that to evaluate this C, okay, it's very length. Hopefully in the future, I can give you the analytic solution, okay, because the solution or the figures that we are using from green, okay, that's an analytic solution, really. So I don't know if we could find some polynomials. So entering with the section area coefficient, the frequency, non-dimensional frequency, and the ratio B over T, we can try to get directly after evaluating these polynomials. It's like a regression, get directly C and A bar. So we shouldn't go into these figures and get the values from the figures. But so far, this is what we have to use. And what I did was, in this case, since I have this constant, this ratio was constant, what I use, I simply get several values and I develop a curve. Okay, so we could interpolate easily with this polynomial. You should try to do something similar to that, okay? Something else that you could do is you could try to implement all of this in a computer code. It's not so long, as you can see. And the main advantage is that, for example, if you try to solve the system of equations, and it's a 2x2, but it's complex, right? So it gives you a hard time trying to figure out how to do it. And if you use programming, it's simple because you can define a variable as complex, and then you simply do an operation as simple as adding two real terms. So it's a good it's a good idea to try to implement this in a computer code. Okay, let's go to group 2. Who is in group 2, people? Group 2? Who is in group 2, people? Come on.
Gutenberg Matute.
Mr. Matute, are you here? Mr. Matute? Mr. Matute, can you hear me?
Listen, you, doctor. We analyzed the coefficients of the question of the B and learn the I33 and B33. But now I don't have my computer sheet, but I can demonstrate that.
I'm not asking. I mean, if you do not do the homework, that's your problem. I'm just wanted to know how far have you come. That's all. Okay, that's all. Let's go to group 7. Who is in group 7? People, group 7.
Carrillo and Niño.
Carrillo and?
Íñiguez.
Okay, Carrillo, Íñiguez, how far have you come?
Hello, Doctor.
Hello.
We have extrapolate for obtain the variable c.
Okay.
For now, we are okay in the mode.
Okay, okay, you feel comfortable, that's fine. I hope with this example, you have a better idea how to complete it. Okay. Mr. Galarza, in what group are you in?
Hello, doctor. We are group number 6.
6. You work with?
Yeah. Michelle Lopez.
Okay, have you done any work?
Yeah. Yesterday we found the fraud degree log and the diffraction components, and we plot that. And we obtain a graph similarly to the one that is in the class notes.
Yeah, okay.
I just have a concern. In the expression of F3, we have a term e to the I omega t.
Okay.
So that term is just
what you do is you take that term outside the integration. And let me see. This is what I have here. So you take this term, e to the I omega t, and it's going to be in each one of these. Similarly here.
Oh, okay.
So you put them outside and you simply cancel. And in the next step, since you have no time dependence, okay, each one of these terms is a constant. Complex, but constant. And you can proceed to solve the system of equations.
Oh, okay, doctor. Yeah, that's my little doubt.
No, I know. It's when you see this, hey man, you say, how can I solve it? Yes, you have to solve it with care because each one of these terms it's complex. So when you multiply two things, you have to be careful not to take simply the real and multiply. No, you have to multiply the two, and after you calculate that, you get the amplitude, not the real part, the amplitude of the complex number. And of course, you can also calculate the phase shift, dividing the imaginary by the real. Yes.
Okay, doctor. Thank you.
Okay. Yeah, but everything is outside E omega t.
Okay.
Miss Freire. Hello, Miss Freire. In what group are you in?
Hi, doctor. I'm in group number 8.
And do you prefer to have the test in person or online?
I think, I don't know, online.
Online you prefer?
Yes.
Why? That's a question I ask everybody in this class at the beginning of the session. That's what I'm asking.
Yes. Well, right now I'm having trouble with the transportation in my house.
Mhm.
So
okay.
that's the main reason.
Yeah, okay,
Mhm.
makes sense, makes sense.
Yes.
Okay, now, in what group are you in?
I'm in group number 8 with Pincay and Jimenez.
So many people. Why 3 people? It's a lot of people. Usually in 3 people, one of them do not work. Who is not working in your group? Mr.
No,
Freddy, Miss
we are
Freddy.
all working.
Nah.
But there are more groups with 3 people. Are like 4 groups.
Mr. Zambrano, what are you saying about that? Can you think that each one person in this group is working?
Yes, I think they are working.
Get out of here. No. Okay, Miss Freddy, what have you done so far?
We have find the constants of this beam equation, the damping and the mass A33 and B33, and the product.
But all of these calculations are for a single wavelength, right? All of these calculations are for one single wavelength.
Yeah.
Okay, remember, you have to repeat the process for other
Yes.
wavelengths. Okay.
Okay.
See, you see here in this slide, I have a lot of numbers, right? And the problem is that, yeah, you calculated, you were supposed to be careful when you calculate, but you're not sure that you did correctly every operation. So every time you can do, try to divide this by any decent or adequate reference value, okay? For example, in the case of the added mass, it's a good idea to calculate the added mass and divide it by the mass, by the dry mass, okay? And more or less you would expect, since the ship is like this, okay, to have a decent added mass. I don't know, maybe a little bit below the dry mass, okay? Similarly for the other coefficients. Okay, now for the excitation force, okay? In this case, when we receive waves from the bow, okay, okay? In this case, in general, we expect the Frode-Krylov component be much, much larger than the diffraction coefficient, okay? And also, you can divide this term by rho g, the area of the water plane, and multiply by the wave amplitude, okay? And in general, okay, this ratio should be less than 1. Okay, similarly for the F5, okay, in the class notes, you have these graphs and making non-dimensional these results. So it's always a good idea, okay? And basically what you are doing is comparing your results against some reference values. It's always a good idea. It's always, it's like it's a mechanical way. You calculate something and you compare it with, for example, at least look at the ship which is on your side, okay? Basically, that's what you have to do all the time. So you calculate the thickness, okay, see, okay, what thickness do you have there? To see if that makes sense or not, because you can see that these procedures are so long. There are so many data you have to consider that it is quite easily to make a mistake, okay? So please try to implement that. Okay, if there are no more questions, then before we break up, the evaluation, the quiz will be on what day, people? Anybody remembers the date?
It says Friday, I think.
It's Friday, yes, next Friday. What time? Does anybody know what time is the evaluation, the exam?
8 a.m.
8 a.m. Okay. Everybody here heard that? Did everybody hear that? next Friday, 8 a.m. Okay. I asked each one of you, and some of you are mostly willing to take the test in person, but there are some others who cannot have problems and prefer to have it at home, online. So as a general thing, we're going to have it online. That's all what we can do. I'm going to ask our coordinator, to Nadia, if it is possible to have the quiz in a hybrid configuration. Okay, I still do not know. Let me ask. So if somebody is in Guayaquil and prefers to come to the university and take the test, yes, you will have the same 2 hours, exactly the same 2 hours as somebody who cannot come to the university. Let me ask. Just let me ask, okay? If there is some possibilities, what I will try to do is I will call you to have a meeting, say Tuesday or something like that, and I will let you know the news if it is possible, right? And if some people have problems, yeah, you can stay home because we understand that, and I will give you the test online. And the other persons, you have to tell me specifically who are going to come. I have to print it and I'll give it to you and you will do it in person. Okay, that's a possibility. So I'm just going to consult, okay? I am not deciding. I'm a dictator. I'm just going to ask because the reasons that you gave me are really solid, right? Okay, but that's all what I can say. Is there any last thought about this, people? Any thought, any ideas about this? Any comments?
Doctor, I use asking about if you can send us some past tests in order to be aware of what we can receive.
Okay, that's a good question. Okay, I'm not going to do it tomorrow or next week. I'm going to do it Thursday afternoon next week, because I don't want you to just review an old quiz and think that you're ready for this one. Remember that in this quiz, you are going to review it in chapter 2 and chapter 3. Okay, and you see that the solution of the last part of this example, which is the solution of the system of equation, is basically what you did in chapter 1. So this is a well-connected course. So basically you have to have a good idea of chapter 1. You are going to be evaluated in chapter 2 and 3, but you still need the 1. Okay, so we have to be clear on that. So yes, I can share with you last year's second quiz, but on Thursday afternoon. So you have to review it, you are ready for the exam, and yeah, the last thing that you can do is you can see what can you expect in an exam like this. And that's all what I can do. I'm not going to give it tomorrow, definitely.
Okay.
Okay, no problem, no problem. Okay, people, if there are no more questions, then I'll see you next. If there is something new, I will let you know, and we can agree on a meeting. And if we have to work in these meetings, I will beg you to try to be in the meeting. So if we are all in the meeting, we can take a decision.
Doctor,
yep.
I want to ask you something from my group. So we have to plot the phase of the exciting force, right? So we could get from the imaginary vector with the arc tangent.
Yeah, but you have to divide the imaginary divided by the real, but you have to be careful with the quadrant in which you are. For example, let's suppose that both terms imaginary and real are negative. The quotient will be positive, and you will obtain a value of the angle between 0 and 90. That's incorrect, because the angle should be between 180 and 270. So you have to be careful with the quadrant. We have mentioned that many times in the mechanical vibrations in chapter 1 in this class. Mr. Zamora?
Yes, doctor, thank you.
Okay. Yeah, because usually, for example, in the case of the Excel, I think you have there is a function which can give you the phase, but you have to be careful. So there is functions that can give you the real part. There is another function that can give you the imaginary part. Get them, you calculate by hand, and then once you feel comfortable, yeah, use the function to calculate the phase using this function from Excel.
And just another question. The motion amplitudes and phase are from the zetas that you show at the last part, right?
Yeah. Remember that if you keep track of the units, right? On the left-hand side, multiply by the Z3 and Z5, and on the right-hand side, you have F3 and F5, right? You solve the system of equations, and the Z3 and Z5, they should have the correct units, but do not assume. Check that indeed they have the correct units. What are the units of C3? Meters. Yeah, but if you keep track of every parameter, yeah, multiply by this, yeah, it has to be equal to that. Yeah, finally, these are the correct units. But don't assume, check.
Okay, doctor. Thank you.
Okay, no problem. Also, if you need office hours, I can be available, say, in the same hours as today. So next Tuesday, I can be available at 4. Okay, from 4 to 5:30 if you want. So this is not an obligation. It's just office hours, just in case you have any questions about the material or the homework. Okay. If you have something extra over the weekend, try to send me an email, for example, Saturday morning. Saturday night, I pachangueo, so I'm not going to see your emails. Sunday, I have to rest. So you either send me an email before noon, Saturday, or at night, Sunday, and I will review it Monday morning. Okay? Yeah, but on Tuesday, I can give you office hours if you want. Okay, people. Bye-bye now.
The doctor,
Yep.
The homework is not for the Tuesday.
I can give you one more day. See, I said it Tuesday because I thought the exam would be Thursday, but since the exam will be on Friday, I can give you until Wednesday night to complete it, because I don't want you to be working on the homework instead of studying for the evaluation. That's what I'm giving you one day before. Yeah, I'll move it up. Move it down, I'm sorry.
Okay, thank you, doctor.
Tomorrow we will be playing basketball if somebody wants to come. Bye-bye now.
Thank you, doctor.
You're welcome.
Doctor.
You're welcome.
Thank you, doctor.
You, doctor, have a good day.